So we're talking about two different classes. We're talking about ODEs and PDEs, and they're both really related to each other, so I'm just clumping them into one episode of 12 classes. So let's talk about it. So the DE in both ODEs and PDEs are basically stands for differential equations. Differential equations are basically equations that involves the derivative. So why do differential equations, ordinary differential equations or partial differential equations, why do they matter so much? Because often in life, it's a lot easier to explain how things change compared to actually explaining the actual numbers or the actual way that the numbers changes. It's easier to describe it through, how the rates of changes of different quantities will occur. So to sort of motivate this idea, I'll give you an example of something that, like a simple case of something that you probably, or at least I've encountered in physics, and that's the case of things decaying. So suppose we have an atom, right? I have an atom of things. Suppose this, or maybe not an atom, but maybe more like a material with loads of different atoms, right? Now, the atom itself, or the atoms inside this material itself, can decay. It can break down and then produce maybe 2 or 3 smaller particles, for example. And then maybe this one also decays, things like that. And the decay sort of happens randomly over time. So that means, like, I don't know if one particle is going to decay this second or it's going to decay the next. That sort of thing. So the question I want to ask is, I want to ask how many atoms will be left after a certain amount of time? Because obviously when the atoms decay, let's just assume it sort of disappears, right? So at least maybe particles fly off, things like that. So I want to work out what the number of particles is over time, or what n is going to be at some certain time t, right? So n is the number of particles, t is the time. So if I just look at this problem and I want to work out what n is, that's really difficult. I can't really do that because, like, where do I start, right? So let's try to think about like how n might change, right? Because that might be a better starting point, a better way to try to understand the problem that we have. Well, how does n change? Basically, what we're trying to think about is we're thinking about what we call the rate of change of n, right? Or dn over dt. Well, what might this be? Well, let's think about, the nature of the decay of the atom, right? The atom sort of decays, randomly. And if the atom doesn't know about, like each other decaying, then when will, the number of atoms decrease the fastest? And the answer would be when there are more atoms, right? So if I have, like here, many atoms, and that means there's loads more atoms who's probably going to just decay just because there are more atoms out there, right? In comparison, maybe if I only have like 2 atoms, right, then, well, sure, one of them might decay at any time, but the chance of one decaying will be a lot less than in this case, because we have more atoms here, more atoms that can decay compared to this case where we only have 2 atoms. So, like, it's a lot less likely to have an atom decaying in this case, right? So we know that the rate of decay, therefore, should probably depend on how many atoms we have. So if you have more atoms, there's going to be more decay. If there's less atoms, there's going to be less decay. So we can say that the rate of change of the number of particles might be proportional to the number of particles that we have, right? So, or dn is proportional to n. dn dt is proportional to n. So, proportionality, we can turn that into an equation. dn dt equal to some constant, we'll call it k, times n, because that's what proportionality means. And because the rate of change of the number of particles should be negative because we have less and less atoms because they all decay, negative sign, things like that. So, that there is a differential equation, and the differential equation comes about from the pictures that we have here, right? And so we can see it's a lot easier to explain, physical systems like these ones in terms of how it changes compared to, trying to just directly work out what n is, because that's a little bit difficult. But if we have this equation, we can solve it. Turns out that the solution will be an exponential term, sort of like that. And that we can come up with the answer there a lot easier, because we have some sort of way to understand the physical world, and that's through seeing how things change. And getting from there to there, that's a whole lot of maths. You can talk about how to do it, there's ways you can solve it, and you sort of learn that in differential equations class. But I think the more important thing that you should take away from like these sort of classes is, having the understanding of how we come up with such equations in the first place. Or maybe not come up with the equations, but at least look at the equations and sort of understand like where they might come from, what they might represent in real life, things like that. So a particular differential equation might have like different derivatives related to each other in an equation sort of way like this. And basically, you can solve them. So the two classes I mentioned are ODEs and PDEs. And the difference is that ODEs talk about what we call ordinary differential equations, and PDEs talk about things called partial differential equations. ODEs, ordinary differential equations, deals with a simpler case of differential equations where the derivatives that you have are basically just regular ordinary derivatives. And so you might have a variable that is related to just one other variable. So for example, y as written in terms of x, and you only want to solve for that one variable in terms of the other. So the equations will only have, for example, two variables that you have to worry about. Now there are many different techniques that you might be able to apply in order to solve one of these equations. I won't talk about what they all are, but basically just, for much of the class you talk about how you might be able to go around and solve one of these equations. Then you also have to talk about other different things about differential equations as well. Things like the fact that differential equations usually give solutions which are not unique. Similar to how when you integrate something, you have a constant which is undetermined. Differential equations, sometimes there might be a constant as well, and then you have to sort of determine the actual solution through different initial conditions. By having an initial condition, you sort of fix what the constant might be, that sort of things. And you also talk about differential equations that you might meet in real life. So of course, physics is just full of differential equations. Everywhere you can write differential equations, you can solve them. But there's also other differential equations in other areas of science and even outside of science as well. Things like chemical reactions, rates of reactions, you can also write them out as differential equations as well, for example. And so you spend a lot of time learning about solving differential equations, and it turns out that differential equations that you can solve is really a really small set. There's only just so many equations that you can solve analytically. You also then have to talk about how you might be able to solve some of these differential equations numerically. In other words, how do I get like just a numerical solution for differential equations without having to find the actual closed form, the actual formula, y equals to something? Maybe just get out the numbers. Maybe that's good enough for some cases. So you spend much of ODEs talking about those, but then you also have PDEs where you're talking about partial differential equations, where your equations, rather than having ordinary derivatives, you have what we call partial derivatives. Now, PDEs are also another entire class of problems, and they're also very interesting. Again, you meet a lot of these in physics, especially when you start to go into higher dimensions, when you start to go into 3 dimensions. Now your functions might not just be in terms of one variable, might be in terms of 3 variables, like x, y, and z, for example. And then these, in order to solve them, you have to use techniques in partial differential equations. Again, there are different techniques you can use to solve them, and we talk about different classes of partial differential equations, many different types. There are, I can't remember the names, there's 3 types of it. I think there's like elliptical, hyperbolic, whatever, etc. You talk about different partial differential equations that we'll see in nature. There are things like the heat equation, there's things like the wave equation, the Laplace equation. I remember it being the big 3 that you talk about. A lot of differential equations other than that will sort of look like that. You talk about what the solutions will look like, and you talk about, you know, how you might go around solving these sort of things. And again, similar to how the solutions of these differential equations are not necessarily unique, you learn about how you get the actual solution if you have, for example, a fixed boundary condition. If you know the actual values for the solution of maybe, for example, the outside at the boundary of the area you're interested in, how can you get the rest of the solutions through the differential equation? And so, as I mentioned, differential equations are really useful in order to describe things in nature, because usually many things in nature, it's just more complicated to describe in absolute terms. It's a lot easier to describe maybe how they change, and this is basically just what differential equations are. And then from there, you may be interested in how the actual solution is, so you can solve them and things like that. Basically, that is like the whole idea of differential equations. I don't feel like this class is like the end of differential equations. I feel like once I start to do more physics, that's where I start to see more differential equations, and then, you know, then you start to solve them, you see how the solutions look like. Honestly, a lot of the problems that you see in differential equations classes in ODEs and PDEs, a lot of the equations are just really complicated equations that maybe doesn't really have any like significant form, or you might not really see them in actual nature. Or what I found is that a lot of differential equations that you do see in nature are a lot simpler than like the equations that you do come up with in like ODEs and PDEs and stuff. But it's still a very interesting class nonetheless. So yeah, that's it for ODEs and PDEs. And tomorrow we talk about another maths class that I've taken that I've really enjoyed.